Hi, welcome. My name is Jon Bodner. I'm a tech fellow here at Capital One, and I'm not a data scientist. But I am someone whose working life is surrounded with data and whose job includes helping data scientists at Capital One get their models to production. And this helps us deliver better products for our customers. And those models are really an important part of Capital One's products and tools. They give us the ability to accurately predict who's going to pay us back. So in effect, my paycheck depends on data science. Please keep up the good work. I'm interested in how to improve that good work. Today, I'm going to talk about how we all fall into the traps that get science wrong and give some ideas that may not get it quite perfect, but at least make things better. So people are, if nothing else, pattern matchers and storytellers. You give us a sky filled with stars, and we make shapes out of them, and we create stories to explain how they got there. And this is good. Discovering patterns is how we learn, and stories are how we share what we've learned. And the history of science is really the history of our progress at finding new patterns that better explain the world around us. And while the history of science is filled with individuals who suddenly notice something that nobody ever saw before, this has become rarer over time. Science today, no matter what the field, is mostly data science. Experiments generate tremendous amounts of data, often using sensors that detect information that's invisible to human senses. And we're utterly reliant on computers to collect this data and to analyze it. And data scientists provide the tools and expertise to process that data, to find the signal, to tell the story, to share the findings. It's a pretty powerful position. The modern world depends on it completely, and not just in science, but in every line of business, from banking to bus routes. And if there's a lot of information and the need to make sense of it, data science is there. And there are many examples of how data science improves our lives, but here are just a few. I'll start with my employer. So back when Capital One was founded, we used an information-based strategy to get the right products to the right customers. And today, we now depend on open source data technologies to process even more information even quicker. And this gives us more insights for our businesses and better meets customer needs. And once you have credit, you can use it to buy stuff. And data science helps here too. Amazon uses data science to optimize every part of its supply and delivery chain. They've even filed for a patent, method and system for anticipatory package shipping. So this is kind of cool. They ship a package to a geographic region based on some data science analysis to show that someone in that region will want that package. And then, while on the fly, when someone actually does order that package, they change the shipping label to actually go to that person. So after you've patented one-click shipping, all that's left really is just no-click shipping. And now for something a little bit more serious, figuring out how to use medicines more effectively. So tamoxifen is a drug that treats breast cancer. And it's well known that in some people, taking tamoxifen will prevent recurrences, but in other people, it doesn't seem to have an effect. And it seems to come down to one particular gene, CYP2D6. And some scientists at the Mayo Clinic went back over studies that had analyzed the effect of this gene on people taking tamoxifen. And they figured out that some studies had used tumor tissue to do the analysis, and some studies had used healthy tissue. And it turns out that if you look at the healthy tissue, it gives a much better indication of whether or not the drug is effective. So this is great news because it means even more people are going to benefit from tamoxifen than people thought before. And there was actually some late-breaking cancer news I couldn't fit onto a slide. Microsoft announced a couple of weeks ago that they think they can cure cancer in the next 10 years by analyzing data using the AI techniques they've developed over time. And this sounds a little optimistic, but it's really impressive, the confidence and the power of data science, right? And all of this is great. Data scientists look at patterns and figure out ways to improve our world. But our need to see patterns and tell stories can lead us astray. Once upon a time, priests would examine entrails to figure out the secrets of the universe. And I'm not really sure how they decided the insides of a sheep were the answer to everything, but I'm sure they didn't do any kind of rigorous statistical analysis on that. And maybe some data scientists could have saved a whole bunch of livestock. But then again, maybe not, because sometimes, despite the best of our intentions, the data analysis confuses noise for signal, and the results are wrong, and the science is wrong, and it's not what we expected. So how common is this problem? It's actually worse than you think. And I started thinking about this presentation when I read an article in The Economist, and anyone at the keynote this morning has probably already heard this. So you're familiar with fMRIs. They give you a picture of what goes on inside your brain when you're thinking about things. It could be like reading Jane Austen or watching a scary movie. And over 40,000 studies have been done with fMRIs. And Anders Elkund at Linköping University in Sweden had an idea. He downloaded the control data from a bunch of these studies and split it up into 3 million different random groupings, and then pushed it through the same software that people use to analyze fMRI data. And this is the control data, so there's absolutely no pattern. And it's across multiple studies. And so given this, you'd expect about a 5% p-value of 0.05, so you expect 5% of the time you'll find a match. Unfortunately, 70% of the time it found a match. So the software kept on finding patterns where absolutely nothing existed. And here's a scary quote from the article. After crunching the numbers, we think that around 3,000 studies could be affected. Without revisiting each and every study, it's impossible to know which the 3,000 are. So the software that's used to analyze fMRIs is questionable. What else has problems? Psychological studies seem to have quite a few problems. There was an article called Estimating the Reproducibility of Psychological Science. It was published by Brian Nosek from UVA in Science in August 2015. And Dr. Nosek and 270 co-authors tried to reproduce 100 different psychology studies. Turned out 36% could actually be reproduced. And his conclusion about why it was so hard to reproduce, there are 3 possible reasons for the results. The original effect was a false positive, his reproduction was a false negative, or both the original and replication results are accurate, but the experiment methodology differed in significant ways. And this is really bad, because if you can't replicate the research because you can't follow the steps to generate and analyze it, the paper's of little value because you don't know whether the reason for the effect lied in those steps. It's another case where you just can't tell that signal from the noise. But psychology is a hard to measure field, right? Maybe there's better luck when you deal with a more solid branch of medical science, like oncology. Unfortunately, there isn't. C. Glenn Begley and Lee Ellis published a letter to Nature in 2012 titled Drug Development, Raise Standards for Preclinical Cancer Research. In it, they reported that Amgen, the big biotech company, they tried to replicate 53 landmark cancer studies. Just 6, 11% of the studies were reproducible. And again, the process seemed to be a problem. Dr. Begley said, for results that could not be reproduced, data were not routinely analyzed by investigators blinded to experimental versus control groups. They sometimes said they presented specific experiments that supported their underlying hypothesis, but that were not reflective of the entire data set. There are no guidelines that require all data sets to be reported in a paper. Often, original data are removed during the peer review and publication process. So yet again, missing steps and now missing data make it impossible to replicate the results. And what's surprising is that all of these problems were predicted in a paper in 2005 by mathematician and medical doctor John Ioannidis. In Why Most Published Research Findings Are False, he described mathematical models that predict the kind of results that are published are almost certainly the kind of results that are false. And this all sounds pretty bad, right? And it might seem like I'm picking on academics. What about corporate data science? Ironically, I'm mentioning the problems in academic medical research because they're the ones doing the best job at uncovering problems and exposing this. If there are almost certainly problems inside of corporations too, it's just that no one's looking for them. If a company has problems with their research and it affects some internal system, no one may ever notice. And if someone does notice, they're not likely to tell the entire world that something wasn't actually working correctly. So if you're doing data science for an internal system that's never going to go public, you need to be extra careful because there are fewer people watching your work. And anyway, everyone here probably heard of this problem before, and it has a name. It's a reproducibility crisis. And there are lots of reasons for this. Some of them are cultural. Publish or perish has encouraged people to try for these astonishing results that may not actually be supported by the data. And journals, they don't want to publish papers that say, I did an experiment and found nothing. And they don't want to publish papers that say, I tried someone else's experiment and it was great. So this is kind of a problem. And there are people who are willing to commit fraud to advance their careers. And these are really tough issues, and I don't have any good answers for those. And other things I don't have answers for is problems with lab process or data collection. As some of these papers mentioned, some of these problems are process-based. And I'm assuming everyone here is doing their best to gather accurate data by following standard practices. Because if the data isn't collected correctly, there's nothing that can be done afterwards to make it better. And I'm sure you've all heard the term for this, garbage in, garbage out. So luckily, if you're working with data from corporate systems, this isn't as likely to be a problem because you can extract it from a database and the sampling isn't an issue. So the things that I'm talking about today are what happens next, doing the right thing after acquisition. The data processing needs to be as rigorous as the data collection was. And I was thinking about these problems with reproducibility in data science, and I realized I'd been dealing with my own version of it for my entire career. I think the first 5 words every software developer learns is, it works on my machine. It works on my machine. Much of my career has been spent either trying to get my code running in production the same way it ran when I wrote it, or looking at someone else's code and wondering why it wasn't working. And the answer is always the same. It worked on my machine. And the software engineering community knows this is a problem. And we've spent the last several decades trying to solve it. And we certainly have not found a complete solution yet. But what's interesting is that we've gotten better at it recently. And we're developing tools and techniques that make it easier to write code that functions the same while you're developing it as when it's running in production. And I thought about these tools and techniques we've been using in software engineering and realized that while there's not exactly a one-to-one correspondence between the problems of data scientists and researchers and those of software developers, there are some similarities. And I bet some of these tools would actually help. So the first of these tools is version control. It wasn't so long ago that most developers would track changes in their code by copying it to different directories on their computer. And if they were really advanced, they'd copy it to a server or a shared disk. And when someone new joined the team, you just say, go to the shared disk, copy it down, and hopefully it's up to date. And if 2 developers touched the code at the same time, the same code, you'd spend days like untangling the dependencies you just put together. So today, software developers, we mostly use version control systems like Git to manage our software. And most data scientists are probably doing something similar for their scripts and programs. How many people here are using Git or Subversion or something else to manage things? Great, that's awesome, that's what I expect. But so when I describe those bad old days of software management, it sounds absurd, right? How can you release code when you can't even find it in the first place? But many data scientists and researchers are still doing similar things when it comes to their data. Even if you start from that known good source, the derived data isn't tracked very well. And if you lose those intermediate transformations, if you can't share that data easily with other people, reproducing your results becomes very difficult. And unfortunately, there's nothing like Git or GitHub for data, nothing that's that popular. But how the data is handled is going to vary from field to field, and it's based on the volume and the sensitivity of the data. People here doing bio or chem research, you have electronic lab notebooks and lab information management systems and scientific data management systems. And all of these help keep track of that initial data collection and manage the equipment in your lab. But only a few of these things will provide solutions for versioning the data after you've collected it and gone through the transformations. If you're doing large-scale physics, like the Large Hadron Collider, those are producing so much data, they actually have to build custom systems to handle it all and actually give presentations on what worked. And those of us who are doing commercial work, commercial companies, they can extract that data from production systems and they can test new data models off of it. But those extracts are often not really managed at all. But this is not an impossible problem. Your processing should be repeatable. Given the same initial data, you should end up with the same end results. If you can store that initial data somewhere, the processing steps that are taken by your programs, your results should be consistent. So in order to make sure when we're developing software that the software builds consistently from machine to machine, developers use build scripts that describe the steps. And data scientists need something similar to a build script to exactly describe the transformations that are performed when going from that initial data to the final result. But if you're not managing that initial data, you're going to have a problem. And there are some startups that are trying to provide tools in this space. And each one's trying to solve some different part of the problem. There's Zenodo, Domino Data, Sense, Plotly, Mode, Alpine Data, just to name a few. None of them have dominant market share yet, so it's hard to place your choices on what you want to stick with. But if you have a company that's using Git, you can try doing this. Git has large file storage that you can enable. And then the initial set of data, you can check it into your repository. And now your data is in a distributed repository with a signature to indicate it hasn't been modified, and it's marked with who checked the data in and when. And if you want to do experiments against that data, you can just create a branch. And you can apply your transformations. And you can check in the transform data you have the new data checked in with a comment that describes what transformations you did. And at each step along the transformations is another check-in. And if it leads to a dead end, that's okay. Delete the branch. And you still have the initial data is still there, checked in, safe and secure. Or if you have two branches of data, you want to compare the results from that, you can do that as well and see how different sets of transformations took you to different places. And once the code and the data are tracked in repositories, it becomes easier to review. And science has been doing this for a long time. It's the peer review process that papers go through before publication. And software engineers have adopted the peer review concept into the code review concept. But there are differences between peer review and code review. Code review happens in small chunks, one bug fix or feature addition at a time. And we don't wait until the very end because it's too hard to look at an entire program and understand what's going on. Peer review in science, it normally happens right before publication. And it's difficult at that point for someone else to get a deep understanding of all the steps that were taken. And especially if the data and the tools aren't available, so the people analyzing your, doing the peer review can't actually understand what all the steps were in between. But to be honest, reviewing everything is a pain, and code review doesn't actually find everything. And it's not always clear just from looking at code if something works correctly. And because of this, software engineering teams usually have testers who write test scripts and manually interact with the application. They click through the UIs, they send commands to the servers, they try to validate that things that were working before continue to work as expected, and unexpected input doesn't lead to strange bugs and crashes. But the problem with doing this by hand is that people are terrible at boring repetitive tasks, like clicking through a UI the same way every single time someone checks in a change. Luckily, computers don't get bored. In fact, they excel at those kind of repetitive tasks that people hate to do. And so test automation has become common with software engineers. We write unit tests that validate that the functions we write, given certain initial data, produce the exact same output. And then we stitch together our tests and create integration tests that check whole modules across each other. And the best thing about this is that all of these tests get run automatically every time we build the software. All that boring work goes away. And data science could benefit from automated test harnesses too. At the very least, that build script I mentioned, you want to run it through and make sure that you can consistently go from that initial data to your final output. If you can't, there's either a bug in your build script or there's a bug in your tools. And if you're able to keep those intermediate stages of data in some repository, then you can test individual transformations to make sure the results make sense. In effect, you've created a unit test for data science. And in order to simplify automated testing, you need to have a defined interface that can be automatically called. So for data scientists, this is going to mean defining a standard specification for what data looks like and how tools are run. And I understand software engineers can be a little too fond of specifications. But we keep going back to them because they give us a good trade-off between solving exactly the problem we have for one particular situation and creating something that other people can understand what we're doing and they can reuse what we've done, and sometimes using it in ways we never thought of in the first place. And the more the data sets are organized according to standards, the more easily tools can be written to work with those data sets, and the easier it becomes for an automated test against the data that comes out to see if there's any obvious problems with your data. And this is a two-way street. The more that tools are written to expect certain data formats, the more easily tools can be shared, evaluated, repurposed, and the easier it becomes to check for errors by writing automated tests that run new and modified tools against known good data to see if the results are improved or if there's actually a mistake. And the kind of tests that can be written are limited by imagination. Has anyone heard of fuzzing? All right, so this is what fuzzing is. Every so often you'll hear a hacking attack in the news where someone put an invalid image into an ad network, and then someone goes in their browser and they visit a web page and it downloads this image and it hacks your computer. It opens up a back door. And this is a really terrible thing to have happen. So what software engineers do to find these kinds of problems is they write tools called fuzzers that just send garbage data into functions to see what comes out. And hopefully the function will see its garbage data and just reject it. And sometimes it crashes in weird ways, and if you're really unlucky, it exposes a security hole. And the programs and scripts that are used by data scientists really should be fuzzed. Once you have these standard inputs and outputs defined, you have a way to write standard programs to send in unexpected data. And hopefully it won't crash, but more importantly, garbage data won't lead to meaningful results. And that fMRI software I mentioned earlier, that's exactly what happened. No one ever tried it with bad data before. And if someone had actually tried bad data earlier, that problem might have been found sooner, and 40,000 more papers might be considered valid. So setting up standards inside of your organization is really just the beginning. If standard data structures and standard tool interfaces are defined for research fields or industries, you can have standard sets of tests and standard repositories of known good data. And if journals adopt them, papers can adopt them, any submitted paper can have its data and its tools validated just as part of the submission process. And so reproducibility stops being something that you consider afterwards at great expense and little interest instead of being a core part of what it means to submit a paper. So the next tool is open source. And the modern software world is built on open source. Even companies that rely on closed source and selling programs, they still live on this foundation of freely available software. And all of this is relatively new. At the turn of the century, Microsoft's CEO was comparing Linux and the open source movement to communism and cancer. And today, Microsoft's the #1 contributor on GitHub. So using code that's open sourced means that you're using code that's been reviewed by lots of other people, and it's code that you can review yourself. And open sourcing your own code allows other people to suggest improvements to your work and to find bugs in things that you've done. And remember, no matter how many smart people are in your organizations, and all of us work in organizations with lots of smart people, there's always more smart people outside than inside. And using open source lets you take advantage of all those people. And for data scientists, using open source falls into 2 categories. And the first is something probably everyone here is already doing. Don't write tools from scratch when you can find a well-vetted open source tool that does what you need. Right? Everyone here is doing that, right? Yeah, okay. And if you can't find exactly what you need, try to start from something existing in open source and modify it. And if you really, really can't find anything, you have to work from scratch, try to open source what you produce. You might think it's unimportant or trivial to solve one small problem, but you might have the solution to somebody else's concerns. So secondly, using open source means open sourcing those data sets and their history of transformations. I do realize that just as companies can't open source all their software, no one's going to open source all of their data. Trivial examples, if you have stuff that has private information in it, it's going to have to be anonymized first. You can't release things that are going to violate people's privacy. And no company is going to release data that it considers a competitive advantage. That's just a given, right? But there's probably more that can be open source than you realize. Any software or data that's used for published papers, really, it should be made as much available as is legally possible. So your work can be replicated by anyone, not just people who are doing that peer review in the first place. And people have been thinking about how to integrate open source with papers for a while now, and there are some interesting solutions out there. You can use your digital object identifiers, or DOIs, to refer back to your code when you reference it in a paper. And if you've released code or scripts on GitHub, Zenodo actually has the ability to integrate with GitHub and generate DOIs for you off of your code, so you can then cite them. And one last thought, just as open source tools can be used by other people in ways their creators never expected, open source data can then be reanalyzed by other people and discover things that the original creator of the data never expected. And this is kind of important. So what about those cases where you can't release your data and your tools publicly? There's still value in inner sourcing. And inner sourcing is a lot like what it sounds like. You take the tools that people use in the open source community, like open repositories and blogs and forums, and you just keep them inside that corporate firewall. It's very helpful, and it's many of the same benefits as open source, is just a much smaller scale, right? So this lets you break down silos inside of your company. People can expose their data and their tools to other people inside. You can start conversations going. And people outside of your immediate team can reuse and retest your work. So in corporations, another idea, when you have that corporate data source that everyone's pulling data from, try to set up a service that wraps it. And this way, this one service can do the anonymization of that data and store it on a server and slice it up by date or line of business or whatever makes sense for you. And if you've defined a standard format for this data, everyone can share it. There's no more of this hiding data in random directories on your computer. You can go back to a single known good source as a place to work from. And talking about open source and its practices, it's hard to believe that open source was actually once considered a fad. But in another way, it's kind of understandable because software developers, we go through a whole bunch of fads. We chase it all the time. And for every good one that comes along, like open source, we have bad ones like enterprise Java beans, if anyone had to deal with those once upon a time. So there is a reason, though, why we do this, why we move from one tool to another. And that's because the world of technology changes so quickly. And as things change, different approaches make more sense. So 20 years ago, when networks were slow and servers were really expensive, we would build giant monolithic apps that ran on one big server. And now, servers are cheaper, networks are fast, so what we do is we'll build lots of little servers that all work together. And they spin up and down based on demand, and it all runs in virtual machines. And this is a better way to solve the problem. And it would be good for research papers to take advantage of modern tools also. Many people still write using tech and LaTeX, and they publish in PDF and HTML. But there have been some experiments with new technologies. From 2008 to 2011, the Optical Society of America and the National Library of Medicine, they published 38 papers using truly interactive science publishing. That's actually what they call this technique. The papers included interactive diagrams and data that are viewable using browser plugins and desktop software. And in 2015, Dr. Michael Ackerman published the results of the experiment, and it was a qualified success. What he said was, truly interactive science publishing was shown to have enough educational value that readers were willing to invest in the needed setup and learning phases. And the social aspects of data sharing and the enlarged review process may be the hardest obstacles to overcome. So there are two things that are interesting about this. First, working on better data sharing and better review process is essential. It always keeps on coming back to this. And secondly, you have to be careful when you pick your tools. Browser plugins and desktop software sounded great in 2008. In 2016, it sounds like another fad. Like it or not, PDF and HTML, they've stood the test of time. And anything that replaces or supplements them needs to be chosen very wisely. But this experiment really should continue. So the right slide. Great. There are interactive tools that have been proven. If you're using Python, I assume a lot of people here are using Python, why not embed a notebook? And this way people can see the code and the data interact. They can see the graphs being generated in real time, right on the spot, and they can play with the numbers and see what happened. If you're doing analysis in Excel, why not publish your Excel files? And the idea is not just interaction for interaction's sake. It's to make concepts that are difficult more accessible to everyone, even to experts, right? And the more people that can understand your paper, the more people can learn from and verify your work, the harder it becomes to hide dubious results. And this only improves reproducibility. So these are the steps that software developers try to follow. You version, build script, review. You run automated positive and negative tests. Stick to standards. Open source what you can. Use open source when you can. Open source what you can. Take advantage of modern technologies. It's not a perfect process, but it has within it the checks and balances that have improved the quality of software over the last decade. And the nice thing about this is that this is a gradual chain of improvements. You don't have to do all of these things all at once. Start versioning your tools and your data. And get people reviewing your code and sharing fixes. And start sharing that code and data in public repositories as much as possible. Start experimenting with new ways to release your data so that it's easier to understand. And some of these things could be done today. Others are going to require the creation and adoption of new tools. And the hardest changes are the ones that require the group action and improvements to existing processes. It's not going to be easy, but this is all really important. So over 30 years ago, Fred Brooks wrote that there's no silver bullet that will solve all problems in software development. And there is nothing that's going to perfect data science either. But adopting these tools and techniques that software engineers have been using can reduce the problems of reproducibility that plague data science and help us find better medical treatments and make companies more efficient and make the world a better place. So thank you for your time. Hope you found these ideas and approaches useful. I want to thank Andrew Sheckman-Rook, Jackie Castle, and Jeannie Drury for their feedback. They helped me to understand some of the problems facing data science, and any remaining mistakes, they're entirely mine. So, any questions?
Question.
Sure.
You mentioned a tool for generating DOIs. What was that called?
Zenodo.
Zenodo.
Yeah, so if you have your code in GitHub already, you can use Zenodo. Zenodo can then link with your GitHub account and generate it and archive it for you and create a DOI of your code. So you can cite it. Yeah. Anything else?
I guess,
Oh?
second question.
Sure.
Are there tools that you can use for fuzzing that generate garbage, or do you generate your own garbage?
It depends. I mean, so for example, like going back to software, if it's images, you can sit there and just like, if you have a JPEG or a GIF or a PNG, you can just generate something that has like a PNG or GIF header and just like call functions and see what happens and see what breaks. And this goes back to defining standards. When your tools expect data in certain formats, you need to, if you can standardize that, the more you can standardize everything, the simpler it becomes to build tools that can be shared. Because a GIF is a GIF is a GIF, it hasn't changed in 30 years. But if there are some places where there are some standards, I understand, in research. But they're few and far between, where people in industry have decided this is how all data must look, and all tools must expect data in this way. And you can build things ad hoc for yourself, for your own programs, and try it out. But the more you can share them, the more you can have this standardized, the easier it becomes. It just builds on top of itself. Yes?
I just have a comment about your fuzzing
Yes?
approach. I really like that. I think it's like kind of like a new approach for a lot of like data scientists.
Okay.
So there's only one concern, because even though you have a negative control data inside,
Mhm.
statistic, you have 5% rate that you basically will show the positive result.
Yes.
So maybe you have to like throw in the negative result there like a couple times and calculate statistics.
Oh, absolutely.
Yeah, make sure like basically it's like that's not common sense for your fuzzing test.
Right, as long as you have that p-value of 0.05 that you want to sit there and beat, then 1 in 20 times it's going to come up good, right?
Right.
So you have to be careful about this and recognize this. And this is I didn't want to talk much about data collection and the submission process, but people do fall in that bad habit. They run the experiment 10 times. It worked once, so submit it. And clearly, those other 9 times had some signal here about this may not be the best solution. But once you hit the results, what you actually submit. And that's what Dr. Ioannidis was talking about when he did his publication, that people submit the good stuff and leave behind all the bad stuff. So, good point. Anything else? Yeah. Sure.
So what if something we intentionally want to hide from? Okay, I know, for example, if I'm a DPM, I know that they have something super portable, that it's some super portable thing as well. I just want to hide that. I'm not proud of it. I don't want anyone else to know what I have done with it. So even if you ask me, I'm not going to say a word. So I know this sometimes happens, like how do you do with it or work around this situation?
Well, first of all, it sounds like a great talk, like how do I hide my mistakes? That would be, may remember that for later. So this is where things like Git actually come in handy. So databases are an interesting case. I don't want to get too software engineering on this. People now will start doing migrations of their database, and they describe in little text files, describe exactly how the database changed revision to revision, and those get checked in and run by tools, so that way you know exactly what happened and when. People who hack the database directly and make changes, that's bad. You shouldn't do that. And the same thing applies to code. Having Git that does a signature on your code every single time really does help, because probably mathematically you can beat the SHA-1, practically you can't. So you know that no one's actually modified. Whatever they've checked in is what actually happened. And we have automated systems that run these things for you automatically. When the deployments aren't done by hand, when it's always a tool doing it for you, this is actually what I've been working with data scientists at Capital One, is getting CI/CD in place, the continuous integration and continuous delivery in place. Then a person can't sneak something in. It went through the whole process, and everything was being pulled from computers along the way. So if someone did something bad, you can look back at the history and say, oh, that's the bad thing, and this is the person who did the bad thing. It really comes down to just getting those processes in place to keep everything tracked. That answer your question?
Yeah.
Okay. Anyone else? Sure.
Not really sure of this topic, but I'm asking, do you have experience with this topic in relation to, not so much, let's say, from an academic space, but let's say Capital One,
Right.
if you have to report your findings to a regulator and have them be able to reproduce and understand it. Have you had any experience with that and trying to get third parties who are responsible for regulating your organization to understand what you did and have some comfort over it?
So this sits into dangerous ground for me. So 2 answers to this. One, I don't have any personal experience with it, and if I did, I couldn't tell you about it. So, but this is a case. I'd want to use Capital One, but any company that has people who have to look at their internal systems and analyze what they're doing, you want to make sure it's repeatable and understandable. And I can't answer anything for Capital One. So, yes, sorry. Anyone else? Great. Everyone gets to go to lunch a few minutes early. Thank you for your time.